where we left off on Friday. We were bringing up this example. What I had mentioned on Friday was that as we've now finished loops and we're transitioning into looking at arrays here, you really have a lot of what you need to be a successful C programmer. The glass half full explanation for that is the optimistic view is, those are the basics, and there really isn't that much more than that. There are a few more things. We will learn them as we go. The more pessimistic view is the reason you have what you need is because such a big part of modern programming isn't really writing the world's most clever for loops and if statements. It's really working with other software. And that's why this lab assignment, as well as where we started to look at it on Friday, is meant to be a representative example of what it means in practice to work with other people's softwares. In this case, to work with a library. So this was the example from Friday where we were doing some very basic image processing. We didn't really get to process any images, so I thought it was appropriate to bring it back up today using the libgd, or the GD library for graphics and drawing. And there's a few different challenges we have to overcome, some of which I kind of solve for you, others that you have to kind of experience yourself. First off, with C at the very least, there's just this issue of how do I get Hello World to work? How do I get the software that I am writing to actually be able to connect to link with the software that somebody else has already written? There's both packages you sometimes would have to install. Replit does kind of take care of that, so we have that sorted for the lab and for this example. There's header files you have to include. Well, how would I know this if I hadn't read some documentation or some tutorial that I have to include that header file for this to work? And then there's just a series of functions that you have to gain some familiarity with, functions and also data types and things of that nature, and just general approaches that the library or other third-party software expects you to be able to use. So optimistically, we've learned what we need to learn. We'll learn more, but we have our basics. The more pessimistic view is, well, now our code isn't that hard, but it's really about reading documentation and tutorials and other people's source code as need be, more so than trying to write really clever if statements and for loops and things of that nature. But this library is quite powerful, and the powerfulness comes from just having a lot of different functions that one can use. I provide links to just kind of the main tutorial and documentation, as well as links to the more specific functions that may be appropriate for our purposes. And where we left off on Friday was just trying to make sure we were all on the same page with regards to, what does it mean to do any sort of image processing? So in this example where we left off, it's doing some stuff with regards to opening files that we have not covered yet, and that was copy-pasted from the tutorial. And if you were to do this, it would be copy-pasted from the tutorial. Yes? Where I'm at right now? The one with the link to all the functions and things like that. The link is available in this Replit project. So if you just open up Lect-05 07 image processing, I provided those links. As well as in the lab for lab 4 part 5, raster graphics fun, I always try to provide that markdown file, that README file that provides that information with regards to documentation and helpful hints. The only part that's a little tricky is that if you don't have that preview button selected, you can't always see what it's meant to look like, which is what this view on the right is, where it's actually rendering the markdown. My intention was not for you to have to look at the source code for the markdown, but just to look at the rendered version of the markdown here. And including there, anything blue is a link that I include because I want you to read that link. And that's the link to the libgd documentation, which is also what we have open here. So on Friday, we walked through the compile steps. And today it's more about, well, how do we actually use some of these functions here? We left off on Friday with opening a file and calling a function that printed out what the input image size was in terms of width and height. Included here are just a bunch of kind of random images, and we had opened up, I think it was just campus.png. So we ran this. The image file was in an image subdirectory, so I type in that name in the subdirectory first because it has to know where to look, campus.png, and so far it says it's opening up the file. It prints out with our printf statement, the input image is of size 1200 by 800. It says processing image, and then done, but we see there's no code there. So processing image done, it hasn't actually processed any image yet. We left off then also kind of having that file open in any sort of like editor or paint type of software. It could be something as advanced as like a Photoshop, but any sort of image editing software, like this is paint.net, would be sufficient for that. And we just kind of zoomed in to make sure we understood what that meant to have this 1200 by 800 image. That is the resolution of an image. It looks like a very nice professional photo. We think of this as being a nice continuous thing, right? We have the green grass and the trees and all the fall foliage and things like that. But ultimately, it's a sample. It's a sample on the camera's sensors that are of a particular size to be able to capture light going through a lens and determining how much intensity of red, green, and blue should be combined together for a particular color at a particular location in that two-dimensional grid. So when we say an image is 1200 by 800, that's literally all that we mean. There's 1200 columns, and there's 800 rows of these pixels. And we can zoom in to the extent that we can see what any of these individual pixels actually winds up being. We'll zoom in on this poor fella walking here on campus. And when it's zoomed out, it looks like two people. I think it's two people. It could just be it's one person walking. But when you zoom all the way in and when you can actually now see these samples, you can think of them as little squares, but what they really are is just a sample of light, right? So we have this little sample of light. Ultimately, that level of detail is kind of a simplification of what our eyes are able to see, right? And so we can look at that particular shirt the person is wearing here. This is just an eyedropper utility, and any paint software would have something like a color picker utility. And we see that what appears to be part of a blue shirt is an individual pixel for which that individual pixel, and I understand you can't read this if the resolution is a little too low on the projector, is stored in a certain format, and there's many, many different formats we can store pixels in. In this case, and for the images we're editing, thinking of them as being a combination of some red data, some green data, and some blue data is sufficient. And that's what's being stored at that location in that particular file. So what we think of as being a blue shirt for that particular pixel is an individual color value that has a red channel or a red intensity of 45. That's out of 255, so a little bit of red, a green of 80, so a little bit more green, and then a blue intensity of 136, so a decent amount of blue. You combine that much red and that much green and that much blue, and you get this color, which is showing here in this kind of color picker space here. You get that color back out. And that's what our cameras are capturing, and they're storing it in that format. And once we have that, we now have these functions in a library like libgd that allows us to say, okay, let me grab those individual pixels, let me do something with them. Let me modify them, let me just change what the ultimate image, the resulting image is going to look like, and I can then do image processing at the very least. While there are more advanced approaches, I can do image processing on a pixel by pixel basis. You can also see, again, the resolution is a little too low. For that same information of 45 red, 80 green, 136 blue, it actually provides a hex code. If you do any HTML or other color pickers, you'll see that, just as we've talked about, hexadecimal is just another way to represent the same kind of data that we can do in base 2 or base 8 or base 10, and that hex code is actually going to correspond to the same information. It's a little bit of red, a little bit of blue, a little bit of green, a little bit of blue, combined together in just a single, in this case, that looks to be like a 24-bit value, because there are 6 hex digits there, so a 24-bit value. So for our code, we already have this function that gives us our width as well as our height. Let's say for that same image, we wanted to analyze, we wanted to print out all of our pixels associated with the image that we have here. We have 1,200 columns, 800 rows. What kind of coding structure would be appropriate for us to kind of iterate across the entire image to grab each individual pixel and print it out? You whispered it, but I believe that you have it correctly. A nested for loop probably makes sense for something like this. There's more than one way one can do it, but we have a function and we copy pasted this in because it looked relevant on Friday. GD, that's the name of the library, image get pixel, and GD image set pixel. So given a pixel or given an XY location, gotta be careful, Y usually refers to this dimension, X this dimension. So that's Y would be our row and X would be our column. And if we get it backwards, we'll get a crash. But I think we'll try to get it right. Given an XY value, it's gonna return back an image pixel value. Don't take my word for it. If we look at the functions in the documentation, GD image get pixel, and here's where you really have to eventually gain more comfort level with reading documentation for functions. Int, it's going to return an integer value, name of the function, has to take this image data structure, which from Friday we have that, so we can just pass that in. The x coordinate x is the next thing we pass in, the y coordinate y. And I would argue the documentation isn't super duper wonderful, but then that integer is likely what is the actual pixel value that's going to get returned back out here. So we can call that. Let's call the function, see what it returns back out. Processing image. So a double nested for loop. I think to that x, y kind of nomenclature they're using here for the x dimension and y dimension, we probably should just use something pretty similar for our for loops. You can use I and j, but then I think there's a likelihood you're going to get confused. If your for loop is ij, but this function is expecting x, y, you might wind up just getting that a little confused. Does x correspond to I or does x correspond to j? The actual order in which we do our loops doesn't really matter, at least from a correctness perspective. Let's assume we're going to go just row by row by row by row. If that would be the case, then our first loop, our outermost loop, would be for the y values. So as we saw, we can declare our variable y. That's going to be our loop iterator just directly inside the for loop declaration itself. You don't have to, but that's a very common coding practice. Gives us the scope of y local to that loop. Y equals 0. Y is less than what? How much can we iterate those rows? Yeah, I wouldn't want to hard code it. That's correct. It is 800 is correct. But I wouldn't want to hard code it because then it would only work for that one image. That happens to be 1200 by 800. So what variable can we iterate until? Image height. Yeah, that's what I would use. There's absolutely no shame in getting your code to work on like a hard-coded example that only works for one image. But then you have to go back and check to see which things have to be more general to work for other images as well. But this should work. And then similarly for our x, that would be less than image width, x plus plus. And we have this function called gdImageGetPixel. That takes that image as input, takes an x and a y value, and returns the integer out. Let's declare it. Let's call it int pixel. That's fine. And we have a loop. It's going to iterate for x equals 0 all the way across. Then for y equals 0 all the way down. It's going to iterate across the entire image. Doesn't do much with it yet. Sure. The compiler will be smart enough that it's not making a new one each time. So we could declare pixel up here, but it's also not going to be necessary. It's limiting the scope of that pixel, which also is probably okay for our purposes as well. That's a good question, but it won't have to reallocate new pixels. We can print it out, right? Print. Image of location is equal to. Well, now we have a little bit of a question of how we actually print it out. but location would be, if we want to stick with Y, X, and then the actual pixel we can print out. Now, it's not clear that we should be printing out these pixels as integers. And actually, we don't know. It's in the documentation for the library somewhere. How do these pixels actually get stored in the library? What data type, and consequently what print format specifier is appropriate for this pixel type? It's in there somewhere. It would take me longer to find it than to just kind of play around with this here. If you don't know, if you know you're printing out some data and you just don't know what format it's in, your best bet is probably to print it out as hex. Not that hex is like magical or anything, but it just doesn't try to interpret this data as anything other than just hexadecimal digits and doesn't worry about it being a signed 32-bit integer or anything along those lines. We can run this code. We have to then type in campus.png. With our for loop debugging, we talked about this last week on Wednesday. What's going to be the downside of this code as we run it? It's going to work, sort of. Yeah, it's going to take forever. But we're not going to be able to wait. Because it's 1200 by 800. That's a megapixel, right? So about roughly 1 million printf statements, and each printf statement's on the order of 50 to 100 milliseconds. That's going to take quite a bit of time to run. We could wait it out, but there's also probably no point. So same when we're debugging our infinite loops, right? There's some value in printing this out. Well, the code's not crashing. That's kind of useful. We printed it out as hex. Just kill it here and take a look at one of those. What do we get back out when we print it out as hex? 1, 2, 3, 4, 5, 6 kind of hex digits back out. It is a good guess, and it is just a guess, that 1, 2, 3, 4, 5, 6 hex digits, we'd be really guessing. Where are we in the image? It actually says at location 112, 424. We can find it. Maybe. It may take us a while. 112, 424, is that what I said? It is library specific. In this case, I believe it's the upper left corner, but I don't know. And if I got it wrong, I got it wrong. 112 by 424. Was that what I said it was? 112 by 424. The problem is this is going to be quite awful. 424 is in the middle of where I have other stuff. 112, 424. Trackpad's not my friend either. We may not get it exactly right, but the nice thing about real images is, nearby pixels should be pretty close too. Yellowish in the tree, we got it. Maybe off by 1 because it starts at 0. Looks different. That's 7F532C. This is definitely a little different, and it's printing a lot of very similar looking values with EC back and forth. You're gonna have trouble seeing it. It's this one up here is one that I'm currently reading off of. I'm seeing brown, goldish kind of colors right here. Well, there's one. Okay, there's one that's pretty close. So okay, it's gold of the leaves that it's printing off here. If you weren't sure, you could take a fully red image and then a fully green image and then a fully blue image, and then it'd be a lot more obvious what the actual result is coming back out. There are also going to then be functions that allow you to look at specifically maybe the red component, the blue component, etc. GD image red, given a color, returns how much red there is. GD image green returns how much green. GD image blue returns how much blue. That could also be pretty useful here. So printing it out is going to be limited. It will take forever. So we have that debug statement, but we don't want to keep it in the code that we want to run here. The example I was showing in the markdown file was an image in which we only displayed the red, the green, and the blue kind of as separate images. And we could probably do that here. So there's a function called GD image red that given a pixel returns how much red there is. GD image red. Do the same for blue and green. And perhaps we could create a new pixel, which, let's see, that's, is that in here or elsewhere, where we want to just grab just the red amount and none of the green and none of the blue. And I've done this before, and you still have to kind of look through the documentation to see which function is doing exactly what I want. GD color image allocate allocates a color given an amount of red, green, and blue. And I went through that very quickly. It's going to return the color value. Let's create a new pixel. I don't know, pixel 2. There's nothing wrong with that function name or that variable name. We're going to call GD color allocate. And for red, green, and blue, we get to specify how much red, how much green, how much blue. If we did red, was it red, green, blue, or red, blue, green? Red, green, blue. If we did red, green, blue, the resulting pixel should be exactly the same as the input pixel. If instead, we don't want any blue, and we don't want any green, we would then have a resulting pixel that has all the red information, but none of the green and none of the blue information. And finally, we want to set the pixel given the image, given the XY location, and the new color that we've created. And because we don't want to accidentally overwrite it doesn't really matter, but let's not overwrite the new image, the previous image, so we have that new one that we copied on Friday. Let's go back through what we just did here. For loop, double nested for loop to iterate across the entire image. So row by row, column by column. Grab the pixel for just fun, I guess. I mean, there's a million things we could do, and there's a lot of really fun functions here. Grab the red component, grab the blue component, and grab the green component. From that hex value it was printing out, we probably could have done our own version of that using the Boolean and or operators, but there's a function that exists. We're going to call it create a new color that has all the red, but none of the blue and none of the green. Store that in our new image that we're going to output back out. Campus, created new image, campus new.png. We have our red campus. And that is the amount of red component in each of those pixels. It's not painting it red, it's just getting rid of all the blue and the green associated with all of those pixels. We can only do so much with campus pictures. I downloaded another one that's also in that folder. Let's open it up with paint.net. If I can. Has anyone had Professor Mina in class yet? Show of hands. A few of you, good. A much more interesting image to process than just a boring old campus image. He looks very confident in this picture here. Ultimately, just pixels. So in theory, we can do exactly what we did before and just change the input image. There was this slight hiccup we had on Friday where the function that's opening up the image cares whether it's a JPEG or a PNG file. So I'll go back to the version because that's a JPEG file. You should be able to run it. It's a different size. This one happens to be 960 by 960. The way we wrote that code, where it's a for loop, x equals 0 to 960, y equals 0 to 960, doesn't really matter. That doesn't really change anything we've done here. Now we have the red, kind of evil, bizarro Mani here. What else can we do with Mani? I'm open to ideas. We could grayscale Mani. There's a couple different ways we can grayscale. Now, built into this library are functions that do a lot of the work for you. GD image grayscale converts an image to grayscale. That feels like cheating almost, but the function's there, so we can just use it. Let's copy it in. He already is kind of grayscale already. It just wears black, all day. So he's kind of a naturally grayscale human. But we could try that. So for that, I would probably comment out. There's no harm in what we're doing here, but I would probably comment out this entire set of for loops, because those are functions that we're calling on a pixel by pixel basis. Looking at the documentation for GD image grayscale, takes in the whole image, just kind of does the for loops for you. I don't know if it's possible, what would it be if we just remove the red and made it 0 as well? Would that be grayscale as well? We can do it manually as well. So let's see if the function that they provided for us grayscales them for us. You can hardly tell. Yes, but he's lost a little bit of coloring. That's really the only way you can kind of tell that their function does work. When we have homework assignments, lab assignments, okay, there's a function that does it for you. I also kind of want you to explore how one would do manually grayscaling. There's actually a lot of different ways mathematically to go from color to grayscale as well as back. One approach would be to grab, let's just say the red, it wouldn't give it the same exact result theirs did, but to grab the red intensity and to make all 3 channels equal to that red intensity, because that tends to be what gray looks like. You wind up getting a gray pixel, and let's see if we can find a reasonably gray pixel here. We'll go for his hair. Gray pixels, again, I'll just read out the numbers. Gray pixels, either from darkest black to whitest white and everything in between, tend to be such that the color intensities are roughly equal to each other. So you can only see the little arrows here. So that's not exactly gray, but pretty close. And that's one way we could set something to gray, although there are many different ways one can do it. If we just grab the red channel, we could say, let's set the red channel, the blue channel, and the green channel equal to that red intensity, and that should give us also a gray Mani. But it won't look quite as good as what the built-in function was doing, because that's a little bit of a shortcut. But it is gray, right? That is kind of a gray result. How about we do gray scale except for his hair? Let's make his hair, I don't know, shocking green. Let's go with that, okay? So color detection is a little bit of a tricky thing. It's something eventually in the classes you take in digital image processing, you'll learn quite a bit of the theory and practice of. For our purposes of like learning how to use these functions and doing something with image processing, we'll kind of hack our way through it, and that's probably sufficient. With an RGB image, he's really staring through me right now. Like he's upset, and now I'm worried he's gonna walk by. Okay, so he won't know that that's him. For RGB pixels, it can be a little hard to answer the question of, is this pixel gray or not? If it's exactly gray, if it's 179, 179, 179, okay, that's easy. But real images aren't so clean, right? Aren't so perfect. What we can probably do is say, if we want to take this image band, one approach, and again, this is a little bit hackish to be honest, but it'll work for our purposes, would be just to kind of color pick in that range and see what we get back out. What we get back out in terms of the R, G, and B values. What's a reasonable range to check for R, G, and B? And if it falls in that range, we would declare, yes, that is a hair follicle that we want to change to be kind of a shocking green or whatever that we're interested in. So that would be my suggestion. We can just kind of pick around, and I'll read these off because I know you can't see them. 187, 177, 142, 161, 155, 129. Looks like we can get away with red in the 140s to 200, we'll say. Let me make a note of that, because this will be a slightly different thing we're doing here. Look for red in the range. Look for Fred too. Look for red in the range, what did I say, 140 to 200. Yeah, and the tricky part is, though, is that his hair is also very much the color of the chalkboard behind it. So I'm going to go for just the light. I'm going to give him some highlights, because as we get older, we need to kind of work on that. I would even go up to 205 and no lower than 140, which is what I said. What about for green? About the same for green. I'll say 150. And they all should be roughly in the same range, right? Because it is gray I'm looking at here. Blue, we're seeing a little bit lower, maybe like 70 to 150. We can play around with this. If we have that, if it's in that range, make it, well, I don't know what color. Make it, let's go, well, I was saying hot green. We'll go hot pink, why not? Let's see. I think it'd be a good look. Trying to find something that looks sufficiently fuchsia here. All right, I like that one. If that's the case, if in range, make the pixel, and there's that hex value that I just copy pasted from the application. We could also have done the red, green, and blue for that, but that hex value will be fine for that. Okay. How would we do that? How do we check? Or I would say, if in range, make this, since we already have that nice gray, otherwise keep grayscale pixel 2, the one that we've already created. How would we do it? We absolutely should. What would it look like? We called it red, yeah. Yep. And I've mentioned that I like to put like parentheses around my clauses just to kind of keep right? Between greater than or equal to 140. You got to remember to include the variable name again. You can't just say red greater than or equal to and less than or equal to. You say the variable. We're checking them kind of separately. Red is greater than or equal to 140, less than or equal to 200. And same for green, right? And green greater than or equal to 150. And this is going to be long, but we'll be all right. Blue greater than or equal to 70. Yeah. No problem. If all that is true, Replit likes to kind of close the brackets for you, but okay. If it's true, what should we do? We're in range. What should we do? Yeah, I would just manually, there's more than one way we can do it. I'll just overwrite pixel 2 if that's the case. We could have done it with an if-else, where we set pixel one way or the other, but in this case, we're saying, hey, if it's in that range, update the value of pixel 2. Otherwise, it's that gray facsimile we created up here. We'll just use that instead. Update every pixel, either with the gray or with that newly fuchsia'd follicle. This never works on the first try, but we'll work on it. That looks terrible. It's kind of like a Mike Tyson style tattoo. What happened? Well, okay. A couple things happened. Obviously, my color code is wrong, so that's not great. But I can sort that out. We can figure that out. We have that color allocate function. Let me just go back and fix that first. That should be fixable. That was the red, green, and blue I wanted. The order of the hex codes must just be different than what this library is expecting. So let's just manually create the color. Instead of the hex code, that comment is wrong. If in range, make the pixel 160, 32, 158. We can do that. Pixel 2 equals GD image color allocate. And we may still get it wrong again, but I'm pretty sure red was first, green. That's pretty standard RGB, red, green, blue, but there are different ways that they can be interspersed. There's no guarantee that's correct, but let's give it a try. It's still going to look bad in terms of the newly found facial tattoo, but the color is about right. Well, the issue is kind of the issue we're facing, that you have the image and we're checking for color bands, and it just so happens that this part of his face is also matching, the part of his hair. How would we fix that? How do we limit it so that we're only doing the region of interest, which is the top of his hair? Yeah, and in this case, for the for loop, we want to still do a for loop because we're processing every pixel. Maybe we check if we're in the range before we do that that color change. We only do that color change if we're in the range. You've got it. It's a great idea. This editor probably is going to be sufficient to tell me. It's giving me the size of the bounding rectangle, which is a little bit less than what I need. Let me see if I got what I'm doing here. This is where the cursor is. So the bounding, assuming that's the region that we're going to do, we can define multiple regions. We are missing a little bit of his hair there, but we'll be fine. Looks like it starts at 176.53 and ends at 568.177. We have to add another comment here to our code, right? So look for if in range, consider y in the range of, what was it again? That's 53 to 178. X in the range, we started at 176 and we're up to 567. 76, 567. Only those. If those are also in range, then we do the processing. Otherwise, we don't do the processing at all. This if statement's already pretty Boolean for my taste. So you could add more Boolean clauses to it if x is greater than equal to this and x is less than equal to that. For me, again, there's no right or wrong to it. I'm just going to do the x and y check first. If y is greater than or equal to 53 and y is less than or equal to 178 and x is greater than or equal to 176 and x is less than or equal to 567. I'm just doing that to kind of clean up my if statement. In terms of what it gets compiled down to, it's going to be very similar, if not identical. So again, you could have made this a massive set of if statements, right, chaining all the way down. We used Booleans to kind of make it somewhat manageable. We're left with one compound if statement that's related to color and one compound if statement that's related to location. I don't love it because it doesn't really fit on a screen, and that's kind of like my goal for the programs that you write, that you can see it, but problem partially solved. See, okay, now it fits on the screen, so we've solved the problem. But it's a bit borderline, but we could justify it. We have some comments. I'd probably want to move the comments closer to the actual functionality. Consider when I say consider like bounding box is what we would call that. Instead of look for, I would say color range, but that's fine. If in range, and it reformatted it so it fit a little bit better on the page. If in range, make that new pixel. Otherwise, don't. Otherwise, just keep the pixel 2 to what it was before. All right, Monty, we want pink hair for you. Nobody tell them about this, please. Thank you. I will deny it. Okay, better. Kind of cut off his forehead a little bit. It's moderately pink. I guess I wish we were a little bit more lenient with regards to the pinkness of it. Okay. We probably could just transform a bigger chunk of it and be. I like what you're thinking. Um, just have a more moderate range of what is acceptable. Let me just chop 40. Let me copy that line because it did work. It made it 2 lines. That's fine. I should have copied it first, and just add a little tolerance to it. This is kind of the fallacy of using RGB to do color selection. It just doesn't work that well, is what you'll find in practice. So let's just make a bigger range. I wanted only 40 on each side. It's going to be 80 now, but that's fine, or 80 total. Since we're using that region of interest, less risk for the rest of the file. There, that looks pretty good. Looks intentional, if you ask me. All right, that's probably enough messing with Mani. Now we can go back to the lab example, which is raster graphics fun. And we start with some of like the built-in task one. Start with some of the provided image filter functions. That's these functions here. Grayscale is fine. They're all fine. Edge detections tend to look pretty nice. If you want to play around with edge detection, well, that's an example, so we don't need to run it ourselves. That's a color edge detection. There's all sorts of algorithms we learn for how to do that appropriately. Task 2, use your for loops. So basically the same thing. Swap color channels, mask out color channels, add some random noise to the image. Once you have an RG and a B, and let me go back to this example that I'm messing around with here. Once you have an RG and a B, and you're creating a pixel based on RG and B, do whatever you want with it now. Let me double the green intensity and add some random noise to the red. You can do whatever you want with them, and you're just setting those pixels at those locations. That's task 2. Task 3, which says start with a blank image and create some sort of interesting pattern. Rainbow pattern should be okay. Sierpinski triangle or fractals, Mandelbrot, there's just equations you follow for how to generate the color at a particular location here. Anything that uses loops is going to be sufficient for task number 3 for that one. Any questions about this example today? Sure. Yeah, and it was a multi-step process. So I would say there are 3 steps required for working with any library. First off, step 1 is the library actually has to get installed in the system. The term people would use is like the development library for a particular functionality. There's oftentimes different libraries or different binaries for using a library versus developing with a library. And in this case, because we're writing our own code, we would need the development libraries for it. Each system that you use for the rest of your life is going to be different this way. That's just the difference between different Linux operating systems and installations or how they manage packages. With our Replit environment, we're using something called Nix, which is a package manager. It's a very clever package manager that is basically you use code to specify what packages you want to have installed. In this case, and that is in the instructions, but reading it in the instruction and seeing it in practice are 2 different things. By adding this line to the package manager configuration file, you were telling Replit, hey, configure this system so that it has this package. Those binaries would not exist if we didn't have that line. So for step 1, you have to actually install the development library. And to be honest, maybe there's a better method, but for me, if I'm on a new system, I have no shortcut other than to Google, what is the name of the development library for libgd on this particular operating system? It happens to be called just GD in Nix. That's great. It's called something slightly different like GDDev or libgddev or capital G, capital D in some other system. And so you just have to kind of discover what it's called and use it there. That's step 1. Step 2, you have to tell the build environment, that's the make file, that's the compiler command line. You have to tell it that when I'm compiling this main.c, I need more than just the built-in boring C standard library stuff, printf, scanf, and the like. I also need to include all the functionality that's in this libgd library and associated libraries. That is usually encoded either in the command line or in a make file. And at least the nice thing about this particular library is that when you go to the main web page for it, the documentation, it does say exactly what it thinks you need to be able to do that part. How do I link in the other library parts that are needed so that your main.c can access those functionality like gd image create and gd set pixel? Syntax is a little unintuitive, but -l means link. Link in this other library. Link in the GD library. Link in a library for loading PNG files. Link in a library for dealing with compression. Link in a library for loading in JPEG files. Link in a library for doing font stuff. We probably are okay if we didn't have that one. And link in a library for doing math stuff. And that doesn't sound super technical, but that's what that is. A library for doing mathematical operations. The best place to encode that to allow your magic run button to still work for this step 2 would be in the make file, where you specify the compiler flags, what things we're passing the compiler. This is the built-in default replit compiler make file, for which we add those same things. And actually I did delete the free type one. We add in those things to the end of that line. Every time you hit the run button and you're compiling, also link in those libraries. There's a couple different places it could have been put, and it's probably going to be okay. For now, it's not. It's frankly, it's not obvious. That's where you put it. Historically, we specified the name of the compiler first. There's our buddy Clang. You call it clang. That's fine. You then specify the compiler flags next, usually. So name of the compiler, the options or flags presented to the compiler, then the name of the file you're wanting to compile. And while it is a little bit hidden what's happening here, that's exactly what this command is trying to do. Give me the name of the compiler, give me the flags I'm presenting to the compiler, the options, command line arguments, the object files, the binaries I want to create, and link it all together. Finally, the last thing you then also need to have is for your compiler to recognize that these are even valid function names, is to make sure you have the header included beyond just the ones we've already been using for other purposes, and those are kind of baked into this system already, that we say that we also need to include these library files. These files they have to exist. If it can't find that, even though everything else is in place, you get all your reg squiggly lines because it doesn't know what that is. It doesn't know what this function is anymore, because where that function is defined in terms of the syntax for it is in that gd.h file. I'm not going to go through this file because this file is probably going to be quite complicated. But amongst many other things inside that file, there's the declaration for every single function you're going to want to use inside that file. So it's those 3 steps. And I do mean it when I say that, reading documentation is a challenge. Looking through tutorials and other people's source code is definitely a challenge. But getting Hello World working for a new library is, in C at least, it's just one of the bigger challenges. It's why when people develop new programming languages and more modern programming languages, that tends to be one of the first problems they try to solve more elegantly than how C solves it, which is discover what the name of the library is, manually install it, or write another piece of software to do the installation for you, figure out what command line arguments make sense to include, figure out which header files are appropriate to be associated with those libraries that you've installed. And only when all 3 of those things are perfectly in place does your button work, does your compilation work, can you get your pink hair from your Mani Mina image. Let's leave things here for today. We'll jump into arrays just starting on Wednesday.